Alright, my name is Kayla Romines, and this is a webinar for Applied Natural Resource Statistics taught by John Zobel on this 27th day of April in 2016. We're going to start talking about bootstrapping as a sampling technique. So bootstrap, what's it for? So it helps determine sampling distribution of means, and this is without assuming normal distribution. So you can use it for non-parametric data or most of all data. So the technique will estimate standard errors based on sampling distribution, which is determined by k-sample means from repetitive sampling, and that's with replacement from the data for a number of times of sample size n. So what this means is observations in each sample. So you're resampling your data. And so k should be fairly large during this. And it can be used, bootstrapping can be used for any statistical measure, such as mean, median, variance, or correlation. Today we'll be using the mean. So just a quick outline of bootstrapping lecture today. We're going to take a look at my brook trout data and execute a bootstrap for the mean to find standard errors for the catch effort of brook trout, and determine the sample size that we need, how many replicates. And then we're going to jump into a little more in depth of R and show you the background of bootstrapping and how it can actually affect your data and give you normal distributions from your samples of samples. So let's take a look at the brook trout data. So here is just an Excel spreadsheet I brought in with the data that I'm going to be using, or at least half of it right now. So we'll look at this first row. We've got stream name, catch effort of brook trout, catch effort of rainbow trout, mean length of brook trout, mean weight of brook trout, as well as the same measurements for rainbow trout. We also have pool frequency, so how many pools there are throughout this 100-meter reach, riffle frequency, and then the sum of those two for the pool riffle proportion. So this gives us an idea of what the habitat actually is. And we have pool mean max depth, riffle mean max depth, as well as total volume. And then with total volume and the frequencies, we determine pool volume and riffle volume, as well as getting into the substrates, which we won't go into depth on. We have slope here for pool and riffle, live canopy and dormant canopy, so just measures of the growing season canopy as well as the dormant season canopy, which is basically rhododendron for this, for the dormant canopy. And then the water quality data was taken at the time of the fish survey, so we got temperature in Celsius, pH, dissolved oxygen, conductivity, total dissolved solids, and as well as number of snags counted within the reach, number of hemlocks counted within the reach, and then hemlock foliage, so how much foliage is left on the hemlocks due to the hemlock woolly adelgid. And so for this study we're going to be looking at catch effort for brook trout. And so we're going to jump on into R. And we'll just clear this out real quick. Start new. So I've already brought my brook trout data in and have labeled it as BKT data. So we'll go ahead and take a look at that real quick. So as you can see here, I've got 11 sites, and you can see all the data here that we have. all the way through it. And so we're going to go ahead and jump into a bootstrap. So to start this function, we're going to start out by doing boot.bkt for brook trout is function bkt.data. So that's your data frame, and then we're going to do a bootstrap for the number of samples we have. We'll do an open curly brace, and so this means that everything within this is one function tells R to run it all together between these two curly braces. And so do m.original, then we're going to be looking at the mean. So this tells it for each bootstrap to look at this. BKT, we'll open up our data set, and we're going to tell it to look at catch effort for brook trout each time. Then m boot equals null. Then for this, we're going to open up a for loop. Pardon me. We're going to open up a for loop where we're telling R what to do for the bootstrap. So we're telling it to do however many times we specify in the index from 1 to mboot, which is the number of times that we're telling it to do the bootstrap, how many samples to take. We're going to open up another curly brace here. We're going to do index is the sample 1, 2, however many rows we have in brook trout data. And looking for the bootstrapped rows, I'm going to look in the BKT data as well. And we want to do this with replacement. So we'll do replace equals true. So now we're going to open up the bootstrap. So we're going to do bkt data dot boot as our new title here for this vector. We're going to do bkt data bracket index, and we'll just leave the y empty. And for mboot again, now we're going to tell it, so it was null before, and now we're going to go to concatenate mboot. So for each of those, look at the mean. We're going to take the mean of bkt data. Oop. Sorry about that. Mean bkt data.boot, and looking at CE of BKT. So that's the brook trout. Once you label it up here, it's going to show up in there as a variable too for catch effort. So that's all of the for loop. So we'll go ahead and close it off. And if we do this, it'll just do it and it won't tell you anything. So we're going to tell it that we want to get the standard error for boot, for the bootstrap. And to do that, we do return data frame. So it's going to create a new data frame with the results. And we're going to call it S standard error boot. And so what standard error boot will be is standard deviation of mboot bias equals m dot original minus mean mboot. And I hope I got the right amount of parentheses there. We'll find out. So we'll go ahead and close this off and we're through with that. So let's run it and see what happens. We'll steal this from earlier. So we don't have any errors here. It's all blue, closed off. That's good. That's what we like to see. We don't want to see any red. So let's take a look at it. So we'll just tell it to run 50 samples right now, and by calling boot.bkt and the data, and then however many samples we want to run. So let's see what 50 will do. So the standard error is 0.028 with a bias of 0.005, so pretty good. And all you gotta do is increase this as you go, and it's going to get closer to the true value. So it's going to take a little longer to run this because it's running 5,000 total samples. So we got 0.0292 now. Alright, so let's jump into kind of what's going on in the background of all this. I'm going to go ahead and clear all this out and start fresh again. So I'm just going to make a vector of 50 variables here to show us, just as an example. Let me do this up here. So I'm just going to do 50 variables from 1 to 50. And you could do this with anything. So I'll go make sure it looks right. Okay, so it made it. X is 1 to 50. Okay. So we're going to take the mean of X, just some background stuff here, standard deviation of X. Then I'm going to go ahead and set the standard error. Do the calculation since there's no function for standard error in R without doing the boot. So that's just going to be the mean divided by 50 times 0.05. So that's going to assign the standard error. We'll take a look at it to make sure. Looks good. Get a mean and a standard deviation. So as you can see there, the variables are mean of 25.5, standard error of 0.0255, and standard deviation is 14.577. So here in the background, we're going to go ahead and do kind of a replicate study here of, we're going to set the seed so we can come back to this if we need to. I'm just going to do today's date, 4/27/15. Call it, we'll just call it junk since we're playing around. Override it. And so we want to replicate this data, and the call for that in R is replicate. And we'll start out with, we'll do 10 replicates. For the mean, sample X 50, and we're going to do with replacement again. And the 50 comes from the number of variables rows we have. And replacement will be true. And so let's just take a look at what this does here. Oh. And so it selected random variables from that data set, and it can replace. So here's 33 and 33, 26 and 26. So you can see that it is actually replacing the values. So if we wanted to do the mean of those random variables, and what the set seed will do is we'll give you these same random variables so you can get the same number out in the end. Otherwise, if we do this again, it'll probably give us new variables or a completely different sample. Yes, as you can see, the numbers are completely different. So each time, so whenever we do the set seed, it's gonna take that first one. We'll take the mean here of this and see what it looks like. Not enough parentheses. We'll just add one in down here. So it's 27.72, so it's a little bit higher than our mean of the whole thing. So we're going to replicate this 10 times and see what we get out of it. For now, we're going to be able to take a look at these. Oh, set the seed. Junk is, so we're going to take the mean of means. And we're going to do standard deviation of the means. The mean of means is 24, so it's a little closer to our actual mean. Standard deviation is 1.47. So let's take a look at this. Well, let's do 100 real quick, or we'll do 50, since that's how many we got. It'll give us a little better look. Okay, so we don't have a normal distribution here, as you can see in this histogram. It's kind of skewed left here, or unimodal. So let's see by increasing the number of replicates if it'll straighten itself out. So let's do 100. So it's getting a little better. The two unimodal's gone, and now it's just got the one mode, but it's still skewed a little bit to the left here. So let's just go ahead and do 10,000 and see if it'll bring it up to normal. And that's pretty dang normal there. So it just shows you how you can replicate your samples of your samples to get a normal distribution, so you can go into work with other statistical practices that require you to have a normal distribution in the assumptions. So let's jump back into this. So what are some of the takeaways from bootstrapping today? So what does bootstrapping do? It resamples with replacement from sampled data. Why? And it's to find standard errors. How does it do this? K times repetitive sample size of n, so your observation. When would you use this? It's most suitable for small sample sizes that struggle to be normal and works its way back to normal with number of replicates. So what's a major advantage? You do not have to assume normal distribution. And so that's my introduction to bootstrapping, and I hope you learned something today. If you have any other questions, feel free to let me know. And thank you.